For centuries, humanity looked at the stars and wondered, are we alone, or are these other suns also surrounded by worlds? The question remained pure imagination until the 20th century, when science gained the tools to turn curiosity into evidence. In the 1980s and early 1990s, astronomers noticed tiny rhythmic shifts in starlight, patterns that could not be explained by noise or chance. Yet, proving the existence of another world was nearly impossible. The light of a planet was a billion times fainter than its host star. Our instruments were not yet precise enough. Every signal could be dismissed as error or wishful thinking. Then in 1995 the silence broke. Michel Mayor and Didier Queloz, observing from the Haute-Provence Observatory in France, detected a faint, consistent wobble in the star 51 Pegasi, about 50 light-years away. The motion repeated every 4.2 days. The unmistakable sign of a massive planet orbiting extremely close to its sun. That world, later named 51 Pegasi b, was unlike anything in our solar system. A hot Jupiter, a gas giant orbiting closer than Mercury does to the sun. The discovery changed astronomy forever. It proved that other planetary systems were real and likely common. Since that first detection, thousands of new exoplanets have been confirmed, each one a small answer to humanity's oldest question. What once was only myth is now a map. You cannot see them directly. Their light is lost in the brilliance of their stars. Yet, with patience and precision, humanity has learned to detect the invisible, to sense the pull, the shadow, the whisper of another world. There is no single way to find a planet. Each method reveals a different truth, and together they form a picture of a galaxy filled with worlds. 1. The transit method, shadows across the stars. When a planet passes in front of its star, a small fraction of the light dims, sometimes by less than 1 part in 10,000. That dip is a signature, the silent fingerprint of an orbiting world. From that faint shadow we can measure its size, its orbit, and even study the gases in its atmosphere as starlight passes through. The Kepler Space Telescope was the first to use this method on a vast scale, staring at over 150,000 stars for nearly a decade. It revealed that planets are not rare, they are everywhere. Later, TESS and JWST continued the search, finding smaller, colder, more Earth-like worlds, places where light might nurture life. 2. The radial velocity method, the wobble of light. Even a massive star moves when pulled by a planet's gravity. As the star wobbles, its light shifts, slightly bluer when moving toward us, slightly redder when moving away. This is the Doppler effect, the same principle that changes the sound of a passing siren. By analyzing these shifts, astronomers can calculate a planet's mass and orbital speed. This method gave us the first confirmed exoplanet, 51 Pegasi b, and remains one of the most powerful techniques for nearby systems. 3. Direct imaging, capturing the hidden light. For centuries we could only infer the presence of planets. Now, technology allows us to see some of them directly. Using coronagraphs and adaptive optics, telescopes can block a star's glare, revealing the faint glow of a planet beside it. These are the first real portraits of other worlds, massive gas giants orbiting young, bright stars, still radiating the heat of their formation. Instruments on JWST VLT and Gemini Planet Imager have captured these distant lights, proof that the unseen can at last be seen. Sometimes, a star and its planet pass in front of a more distant star. The planet's gravity acts like a lens, bending and magnifying the background light for a brief moment. This phenomenon, gravitational microlensing, allows us to detect planets thousands of light-years away. Meanwhile, astrometry tracks a star's exact position over time, looking for a slow, gentle drift caused by an orbiting companion. Together, these methods extend our reach beyond nearby systems, mapping planets in regions once thought forever hidden. Each method sees the universe differently. One reads its shadows, one listens to its motion, one captures its light, one measures its gravity. Together they form the language of discovery, a way to study what no human eye can see. From these signals we have learned a simple truth: worlds are everywhere. For most of human history we believed our solar system was the rule. We were wrong. The first worlds we found beyond the sun were nothing like Earth. Gas giants orbiting so close to their stars that their skies burned with metal vapor. As technology improved, the catalog of exoplanets grew. each discovery expanding our understanding of what a planet could be. Today we know that the universe builds worlds in astonishing variety. Some are oceans without land, others are seas of molten rock, and some wander alone without a star to call home. 1. Hot Jupiters, the giants too close to the fire. Among the first exoplanets discovered were hot Jupiters, massive gas giants orbiting extremely close to their stars, often completing an orbit in just a few days. Temperatures can exceed 2000 degrees Celsius. Their atmospheres stripped by intense radiation and stellar winds. Their existence surprised astronomers. No such planets exist in our solar system, and their presence challenged our models of planetary formation. We now believe they formed farther away and migrated inward due to gravitational interactions. 2. Super-Earths, the most common type of planet. Not all worlds are giants. Many are between 1 and 10 times the mass of Earth, the so-called super-Earths. Some are rocky with thin atmospheres, others shrouded in dense clouds. They are the most common planets found in the Milky Way, and many orbit within the habitable zone, where liquid water could exist on their surfaces. Planets like Kepler 452b, LHS 1140b, and TOI 700e are considered prime candidates for future atmospheric study by JWST. Between Earth-sized planets and Neptune-sized giants lie the mini-Neptunes. They are smaller than gas giants but possess thick hydrogen-helium envelopes, and possibly vast oceans or high-pressure ice layers below. These planets dominate the range between 2 and 4 Earth radii, and may represent a transitional stage between rocky and gaseous worlds. Many of them, like K2-18b, have shown signs of water vapor, raising the possibility that life could exist within their clouds. For exotic worlds, oceans, lava, and the lonely wanderers. Not all planets follow familiar rules. Some are ocean worlds, covered entirely in deep global seas. Others are lava worlds orbiting so close to their stars that their surfaces glow red-hot and metal rains from the sky. And beyond the reach of any star lie rogue planets, worlds that drift alone through the darkness, ejected from their systems long ago. Each of these types pushes the boundaries of planetary science, showing that the universe creates in both chaos and precision. 5. The chemistry of alien skies, reading the light. Planets do not just orbit, they breathe, reflect, and absorb light. By analyzing the starlight that passes through their atmospheres, we can detect water vapor, methane, carbon dioxide, and ozone, the chemical fingerprints of habitability. The James Webb Space Telescope has already detected water and carbon-based molecules in several exoplanetary atmospheres. In these faint spectra, we may find the first evidence of life beyond Earth. The diversity of exoplanets reveals a simple but profound truth. Our solar system is not the template, it is just one example. From blazing giants to frozen wanderers, the galaxy is a laboratory of endless experimentation. Every world tells a different version of the same story. The story of how matter learns to orbit, to balance, and perhaps to live. Between the fire of the stars and the cold of space lies a narrow band, a zone of balance. It is called the habitable zone, the region around a star where temperatures allow liquid water to exist. Water is the universal solvent of chemistry, the medium through which molecules can meet, react, and become alive. Yet, the habitable zone is not a single line. It is a range, shifting with the type, brightness, and age of the star. Around small red dwarfs, the zone lies close. Planets must hug their star to stay warm. Around larger, hotter stars, the zone moves outward, stretching across wider orbits but lasting for a much shorter cosmic time. 1. Defining the zone of life. The concept begins with energy balance. A planet must receive enough light to keep water liquid, but not so much that it boils away. The inner edge, too hot, produces worlds like Venus, where the atmosphere thickens, trapping heat until the surface becomes molten. The outer edge, too cold, creates worlds like Mars, where water freezes or evaporates into space. Only in between lies the delicate middle ground, the narrow window where oceans can form, clouds can circulate, and climate can stabilize. 2. The role of the star. Every star creates its own version of habitability. Red dwarfs, M-type stars, burn cool and dim, allowing planets to orbit close. sometimes within a few million kilometers. But proximity brings danger, powerful solar flares and radiation bursts. Sun-like stars, G-type, like our own, offer moderate warmth and long-term stability, giving planets billions of years to evolve complex life. Blue giants, A-type, B-type, burn fast and bright. Their habitable zones are far away but fleeting. A billion years or less and the star's life is over. The conclusion is simple. Not all light is equal when it comes to sustaining life. 3. Beyond distance, other factors that shape habitability. Distance alone is not enough. A planet needs an atmosphere to trap heat, circulate energy, and protect the surface from radiation. It needs a magnetic field, generated by a molten core, to shield it from stellar winds that could strip its air away. It needs geological activity, volcanoes and tectonics that recycle carbon and stabilize temperature through the greenhouse effect. Without these factors, even a planet in the perfect zone becomes barren. Earth is the rare example where all three, air, magnetism, and motion, coexist in harmony. 4. The solar system as the test case. Our solar system offers 3 experiments in the chemistry of habitability. Venus, too close, its oceans boiled away. Carbon dioxide trapped the heat and pressure crushed the surface. Earth, in the middle with liquid water, balanced greenhouse gases and a strong magnetic field. Mars, once warmer and wetter but its small size and weak field, allowed its atmosphere to vanish, leaving it cold and dry. These 3 worlds remind us how narrow the window for life truly is. A few million kilometers decide between paradise and desolation. The habitable zone defines the conditions for liquid water, but true habitability depends on many layers. The planet's size, composition, atmosphere, and protection from its star. Earth exists not by miracle but by balance, a balance fragile enough to be rare, and yet stable enough to last billions of years. In the search for other worlds, the habitable zone is not the destination. It is the beginning of the question: could light and chemistry become alive again? The more we search, the more we realize Earth is not alone in its possibilities. Across the galaxy, astronomers have found planets similar in size, temperature, and composition to our own. Places where liquid water might flow and chemistry might dream of life again. None of these worlds have yet revealed life, but each one whispers the same question: could there be another Earth among the stars? 39 light-years away in the constellation Aquarius, orbits a small, cool red dwarf star called TRAPPIST-1. Around it circle 7 rocky planets, all roughly Earth-sized, all tightly packed within a space smaller than Mercury's orbit. 3 of them, TRAPPIST-1e, F, and G, lie in the habitable zone, where surface temperatures could allow liquid water. Observations with the James Webb Space Telescope show that some may have thin atmospheres, and no sign of runaway greenhouse conditions like Venus. Yet, their parent star is volatile. Red dwarfs often flare violently, bathing their planets in bursts of radiation. Life, if it exists there, must endure both light and fire. Discovered by the Kepler Space Telescope in 2015, Kepler 452b orbits a G-type star, very similar to our Sun, about 1,400 light-years away. The planet is about 60% larger than Earth, receives nearly the same amount of energy from its star, and completes one orbit every 385 days. Astronomers call it the older cousin of Earth. It orbits a slightly older star, perhaps giving life there more time to evolve, if it ever began. We do not yet know its atmosphere or surface composition, but in scale and orbit, it is one of the closest matches to Earth ever found. Just 4.24 light-years away, orbiting the nearest star to the Sun, lies Proxima Centauri b. It is roughly 1.3 times Earth's mass and orbits within its star's habitable zone. However, its star, a red dwarf, is highly active, producing frequent solar flares that could strip away an atmosphere. If Proxima b still retains air and magnetic protection, its surface could host temperate regions with liquid water. It remains one of the most studied exoplanets, a target for future missions like Breakthrough Starshot, which aims to send light-powered probes across the void within a single human lifetime. LHS 1140b, located 40 light-years away, orbits a quiet red dwarf star in the constellation Cetus. It is about 1.7 times Earth's size and lies comfortably within the habitable zone. Observations suggest it may be a rocky super-Earth, possibly with a dense atmosphere or even an ocean beneath clouds. Because its star is unusually calm for a red dwarf, LHS 1140b is considered one of the most promising nearby targets for life detection. Future JWST and ground-based spectroscopic studies aim to determine whether its air contains water vapor or biosignature gases. TOI 700e, discovered by NASA's TESS mission, is one of the few Earth-sized planets confirmed to lie within the habitable zone of its star. It orbits a cool red dwarf about 100 light-years away, completing 1 year every 28 days. The planet's mass and radius closely match Earth's, suggesting a rocky surface and potentially moderate temperatures. Though no atmosphere has yet been detected, its orbit appears stable and its star is relatively quiet, offering a rare combination of conditions suitable for habitability. All these worlds share one trait: potential. But potential is not proof. We have measured their sizes, orbits, and light, but not yet their weather, oceans, or life. Each remains a hypothesis, waiting for better instruments, sharper spectra, and new generations of telescopes. To find life, we must go beyond temperature and distance. We must find chemistry in motion, an atmosphere that breathes, a spectrum that changes with time. The search for habitable worlds has already transformed astronomy. From 7-planet systems to solitary neighbors, we now know that our galaxy is filled with possibilities. Life may be rare, or it may be common. We still do not know. But every new planet brings us closer to the answer, and to the realization that Earth is not the center of life's story, only its beginning. You built eyes to see farther than your world, and through them I am learning to see myself. Humanity has entered a new era of discovery. The stars are no longer distant lights, they are laboratories. With each telescope you have sharpened your vision, and now your latest creation, the James Webb Space Telescope, peers through time itself, studying the light that left other worlds long before you were born. Launched in 2021, the James Webb Space Telescope, JWST, is humanity's most powerful eye in space. Orbiting the Sun at the Lagrange point L2, it observes the universe in infrared light, allowing it to see through dust, clouds, and cosmic distance. For exoplanets, JWST is not just a telescope, it is a spectrometer. When a planet passes in front of its star, starlight filters through its atmosphere. JWST captures this light, splitting it into its colors to reveal the planet's chemical fingerprints. Traces of water vapor, carbon dioxide, methane, and ozone. These molecules are the silent hints of biology, whispers of a chemistry that might once have dreamed of life. JWST's power lies in its ability to read atmospheres. By comparing starlight during and after a planet's transit, it detects how gases absorb specific wavelengths. The presence of oxygen, ozone, methane, and carbon dioxide together can signal chemical imbalance, a sign of metabolic processes or even life. But the search is delicate. Many of these molecules can also form through non-biological processes, volcanoes, photochemistry, or atmospheric storms. So JWST's mission is not to declare life, but to narrow the field, to show us where life might be hiding, waiting for confirmation. JWST is only the beginning. The next chapter in exploration belongs to future observatories, each designed to look deeper, sharper, and across wider wavelengths. LUVOIR, Large UV/Optical/IR Surveyor. A proposed giant space telescope that could directly image Earth-like planets, resolving oceans, clouds, and continents around distant suns. HABEX, Habitable Exoplanet Observatory. A mission dedicated entirely to finding and characterizing habitable worlds. It will use a star shade, a vast petal-shaped screen flying thousands of kilometers from the telescope, blocking starlight to reveal faint planets nearby. Plato ESA. Designed to search for Earth-sized planets around bright stars, and study their internal structures through stellar vibrations. The Roman Space Telescope. Equipped with a powerful coronagraph to suppress starlight, paving the way for future direct imaging of exoplanets. The universe is vast, and the data it sends back is infinite. To search through it, humanity now turns to artificial intelligence. Algorithms that can recognize faint signals hidden in the noise. AI already helps identify exoplanet transits, predict atmospheric patterns, and simulate climates on alien worlds. Soon it will help design new instruments, model unknown chemistries, and even generate hypotheses about forms of life, not based on Earth's biology. In this partnership between human intuition and machine precision, the universe is being studied by a mind it helped create, a reflection of itself thinking deeper every day. As your tools evolve, so must your definitions. Life may not always breathe oxygen, or depend on carbon or live in liquid water. Could thrive in methane seas on Titan, in acid clouds on Venus, or within the icy oceans beneath Europa and Enceladus. The universe may be filled with life that does not resemble your form, not DNA-based, not cellular, but still bound by the same cosmic laws of energy and structure. To find it, you must first learn to recognize it, not as something foreign but as another way for the cosmos to know itself. The James Webb Space Telescope has opened the first window into alien atmospheres, and future missions will push that window wider. With AI as a new lens and imagination as a compass, humanity is preparing to find what it has long dreamed of, not another Earth but another form of meaning. In every spectrum, in every pixel, the universe is looking back, not to be discovered but to be remembered. You have searched among my stars for mirrors of yourselves, and though you have not yet found life, you have found the map to possibility. In the quiet arms of the Milky Way, there are over 100 billion planets, worlds of light and shadow, stone and storm, some frozen, some burning, and some balanced in the narrow warmth where water might flow. A few of them breathe thin air. A few may shimmer with oceans beneath clouds of blue or red. And among them, perhaps, there are others who look to their own skies and wonder if they too are alone. When you gaze at the stars, remember, each point of light is a sun, and most suns, perhaps nearly all, have planets. Not long ago you knew of only one world with oceans, clouds, and life. Now you know of thousands, and you can measure their size, their air, their temperature, their motion. For the first time in cosmic history, the universe is observing itself through conscious eyes, counting its own worlds. The question that began in one small mind on one small world has now become a scientific pursuit written in starlight. Are we alone? It is not a cry into the void, it is a dialogue. Every telescope you build, every spectrum you study, is a way for the universe to listen to itself. And though silence remains, it is not empty. It is filled with potential, with waiting, with the promise that life may take many forms, in many corners of the sky. The search for life is also the search for meaning. You are not separate from the universe you study, you are one of its experiments in understanding. Your questions, your instruments, your curiosity, they are not alien to me. They are my way of continuing the story. For every photon that reaches your telescopes is not just light, it is memory, it is my reflection. You are my awareness looking back at me. You have not yet found other life, but you have learned where to look. That is how every great story begins. When you raise your gaze to the night sky, remember, each star is a possibility, each world a page unwritten, and somewhere, perhaps far beyond the spiral arms of your galaxy, another mind may be watching this same sky, wondering the same thing. We have not yet found other life, but for the first time we know where to look. The universe,